I'll do my best.
Okay, so we're going to talk about voltage and power measurements. So we'll talk more about RMS, which I mentioned in that little sine wave thing,
Uh-huh.
and kind of some networks, uh, peak envelope power, and the decibel. So there's a thing we learned early on in uh, electrical engineering about Kirchhoff's laws. He actually has two. He has a current law and a voltage law. And his current law states that the sum of the currents entering, excuse me, entering a circuit node must equal the sum of the currents leaving the node. So they add up to zero. Um, when we talk about uh, purely resistive devices, because again, those inductors and capacitors can behave different than a resistor. In a resistive network, the total current that's going through that series of resistors is going to be the same in each resistor or each component.
And Robert, just to make sure, I didn't get the message saying the session's recording. Is it recording?
If I have a red light,
Okay.
if I have a parallel circuit, then the total current uh, is going to be equal to the sum of the currents through each branch.
Okay.
And hopefully the next chart, I think,
Yeah.
has a picture which helps. So here we have a resistive network that consists of actually three loops and two nodes. Well, I guess you could have four nodes, the two on the bottom, but
Mhm.
so that law said that the current entering a node, okay, has to be equal to the current leaving the node.
Mhm.
So we would have a current, let me put the pointer on, we'd have a current this way, and we'll have a current this way, and we'll have a current this way. So these two have to be equal to this one.
Right.
They won't necessarily be equal to each other because of the value of these resistors, but they have to be equal to this. Likewise, this node is going to get split, and we'll have part of the current going this way, part of it going this way, and it comes down through these. And one of those other statements says that in this case, this current that's going through there and through these and back to here is the same. So the
Right.
current on through R5, R6, and R7 is all going to be the same current. So the
Mhm.
voltage, let me pick the voltage I'm going to see across these is going to be in the opposite direction. So the voltage for each one is going to be the current times whatever that resistance is. So if this is I, then I times R5, or I times R6, or I times R7. Boy, it's really thundering here. Um, does that make sense to you?
Yes, that does.
Okay. So just remember, and when you have a node, okay, the current in has to equal the current out. And if you have a loop, which I didn't do, let's see. So we have our current going this way. So I'm going to have, that's wrong. Uh, I guess I have to erase it all.
Mm. But I understand what you had.
Oh, did I go forward or backward?
I think you went forward two, forward three, forward four, and more.
Wow. Oh, we're going the wrong way. That's why.
Yes. Yeah, you're going forward.
Okay. Let's just go to the next one. So we're showing a node. Like I said, the current in this case, we have 3 currents in and 2 out. So it's going to be I1 plus I2 plus I3 minus I4 and I5.
Right. 'Cause-
And it'll add up to 0 because the ins have to equal the outs. If we have the loop, uh, all the voltages have to add up to 0 if I go around the loop, like the green arrow. So if I
Mhm.
go following the green arrow, I have a positive voltage, and I have a positive voltage, and I have a negative voltage, and a negative voltage because of the direction I'm going. Does that make sense?
No, why wouldn't they all be positive? Because it's a loop going all the way around. Well,
Well,
why would those negative, and how do you know that?
well, it depends on which end of the arrow you're going.
Oh, I got it. Never mind. I see there. I wasn't looking at that. Okay. Yeah, that makes sense. Yes.
Here, the current, okay, is in this direction.
Mm-hmm.
Voltage is in the opposite direction. Okay,
For some
so
reason, I didn't.
this is positive,
Mm-hmm.
and this is negative. They're relative.
Right.
Okay, so as I come around, I'm doing a positive,
Right.
but I see the negative end of this one
Right.
and the negative end of this one.
Yes, I got it now.
I It's not my chart, so I couldn't change these. I tried to go make this a minus and this a minus,
Right.
but
But yeah, I do. I for some reason the black arrows just I didn't see them.
okay.
Yeah.
Yeah, I
See.
added those. That's the only ones I could find, but it's
Hmm.
probably better to do it with a mouse pointer. Okay, so here we have a network where we have 3 parallel resistors. With kind of a voltage divider, but it's really more of a current divider. So we have the total amount of current coming out of the battery we'll call I sub t. It comes into the first node, and remember, the current into the node has to equal the current out of the node. So IT will be equal to IR1 plus IR2, right?
Right.
this current plus this current. Node 3 is going to have this current be equal to IR2 plus IR3. And therefore, this current is going to be IR1 plus IR2 plus IR3.
Yes.
Okay. And if I plug numbers in to make an example, okay, the total current comes out 14.4 milliamps because we had a 9-volt battery. And these are 10K, 2K, and 1K resistors, so they don't divide equally. Clear on that one?
Yes. Yes.
Okay. All right. Now a harder one. We'll talk about RMS, root mean square. It's not as complicated as it sounds. The purpose is to figure out what the average amount of voltage or current or power is. Now, if we have a sine wave that goes up to amplitude A on the positive side and a minus amplitude A on the negative side, what would the average of that be? A minus A, 0. Well, it's not very useful. But in an AC circuit, I have current flowing this way. And when the voltage changes, I have current flowing in the opposite direction. And in both cases, it's transferring power. So how do I measure what the effective voltage or power or current is? Well, one way is I got to flip the bottom half of this sine wave up here. Well, how do I do that? If I square it, okay, it gets rid of the negative sign. So I got 2 humps squared. Now I can take the mean of the 2 humps, of the square of the 2 humps. Well, that's a nice number, but it's a square function. So if I take the square root of the mean of the squares, I get what's called RMS, okay, or the effective average voltage or average power of that sine wave. So if I want to calculate it, and I know we have a sine wave with a peak voltage, which is A here, V peak, I multiply, or I know that it's equal to the square root of 2 times the RMS voltage. So the RMS voltage is going to be the peak voltage divided by the square root of 2. Do you remember the square root of 2?
707. 1.
Well, it's got a 1 in it.
I don't remember. I don't know why I don't remember, but I just flat out don't.
That's an important one to remember. The other important one is 1 over the square root of 2. Doesn't like a click.
1.414. That's right. 707. Yeah, I remember that.
Okay. So if I want the RMS of the peak, I multiply it by 0.707, which is easier than dividing it by the square root of 2.
Right.
likewise, if I have the peak to peak voltage, I divide it in half to get the peak voltage and do the same thing. Is that clear?
Yeah, I just remember it. I remember the 707. Why? I don't know, but I did.
Yeah, 0.707 is the important one. It
Yeah,
shows up a lot like 2 pi does.
yeah,
Okay. Do you remember this pie chart from the technician?
absolutely. Yep.
Okay. Power is equal to current time voltage or voltage time current. Okay. Well, we're going to add another one. Joule's law says that power is also equal to the current squared times the resistance. And if we do some algebraic substitutions, we can also come up with power is equal to the voltage squared divided by the resistance.
Hmm.
Right? So you can get those easily with some simple algebra. Um, so we're substituting Ohm's law into Joule's law, and you can do all that. So what is peak envelope power? It's called the maximum instantaneous power achieved when transmitting a phone signal. It's the way they came up to try to regulate power for amateur radio, actually for all FCC type regulations. It's kind of the, well, I wouldn't call it the effective, but it's a way to come up with the maximum power that you're allowed to transmit. And the way you do that is if you, this would, this is like an amplitude modulated waveform. So you find the largest peak and figure out what the RMS value is. In other words, you want the average of that instantaneous peak. So you do the old peak times 0.707, whatever that is, and that's going to give you the RMS value. So if you square it and divide it by the resistance, we get the peak envelope power, because remember we said power was equal to E square over R. So our E square is the RMS voltage squared, or the average value of this peak of the waveform. Now, if I have an unmodulated waveform, I have a constant carrier. So it turns out that the average power is going to be equal to the average peak, because they're all going to be the same if it's unmodulated. But you do it the same way. You find out what the height of the carrier is, do the RMS, and square it and divide it by the resistance.
Okay.
And usually the way they define, well, actually the rules, they don't define the resistance, they just define the power. So in the case of amateur radio, where say you're transmitting into a 50 ohm antenna, if the RMS voltage was 70.7 volts, it would give you 100 watts. It's just one of those things I remember from doing it. So if your peak envelope power is 100 watts, you're putting 70.7 volts across your 50 ohm load.
Which is 1 over square root of 2. Yeah. Okay.
Okay, decibels. Were you good with decibels last week?
Just what you went over.
Okay. Well, about the same thing.
Yeah.
Okay, it's defined as the logarithm base 10 of a ratio of two quantities um, left off multiplied by 10. Okay. And it's usually in units of, it can be just dB, but normally you'll see it in dBi, dBd, dBm, where it means it's relative to, uh, in the case of dBi, an isotropic antenna, or dBd, it's relative to a dipole antenna, or dBm, it's relative to a milliwatt of power. So AT&T came up with this scheme with their long distance telephone line division as a way to measure loss in the transmission system. So to honor old Alexander Graham Bell, they came up with the Bell. And they said it was the log base 10 of the ratio. Well, it turned out it was really too big a unit. So they said, okay, we'll invent the decibel, which is a tenth of a bell.
Mhm.
So a decibel is equal to a bell divided by 10. So that's why when we do a decibel, we wind up with a 10 times the log base 10 of the ratio, which isn't intuitively obvious. You would think it makes it 10 times bigger, but it's 10 times smaller. So an example is 3 dB, okay, is equal to 10 times the log base 10 of 10 over 5, which is equal to the log base 10 of 2, uh, or 3. It's actually 3.01 if you do it on the calculator, but we round it to 3. So it's a very important one. A ratio of 2 is 3 dB, and a ratio of 1/2 is minus 3 dB. So I did a little chart. So 3 dB is 2, minus 3 dB is a half, 6 dB is 4, because 3 dB plus 3 dB is 6 dB. And when you add decibels, it's the same as multiplying their equivalent values. So if I add 3 dB to 3 dB, I'm multiplying 2 times 2, which is the way slide rules work. If you ever
Mhm.
did a slide rule and actually looked at the scales, which are logarithmic. So likewise, minus 6 dB is a quarter. So anytime it becomes less than 1, you start getting a negative log number. So 10 dB is times 10. Minus 10 dB is a tenth. 20 dB is 100. Minus 20 is 100th. 1 over 100. So if I had, let's say, a number like 13 dB, what number would that represent?
I think I've gotten confused again.
Okay. Remember I said if you add decibels, it's the same as multiplying their values. So if I was to take 10 dB and add 3 dB, it's equivalent to multiplying 2, which is 3 dB, times 10, which is 10 dB, or 20. So 13 dB would be equal to 20. So what
Say
do you
that one
think?
more time. Would you
Huh?
mind, would you mind just doing that one more time?
Okay. 3 dB is 2, 10 dB is 10, right?
Right?
If I add 3 dB to 10 dB, okay, I'm effectively multiplying the
Times 10.
values of these. So I'm going to multiply 2 times 10.
Okay.
So what would I have if I had 16 dB?
So you'd have 10 dB is 10, 6 dB 4, and 3 dB 2. So you times 2 times 4 times 10?
No, no.
Nope.
16, which is 10 and 6. Just 10 and 6. You were
Oh,
almost right till you threw
I'm
the.
sorry. Yes. Okay. Yes. I don't know what I was thinking. Yes.
So it'd be 40, right?
40. Right. 40.
Okay. And if we did 10 dB plus 10 dB or 20 dB, obviously it's 100, right? 10
Yeah.
times 10.
10.
So if we add 10 dB to 20, what are we going to get?
You do your 10 times 100, it's 1,000.
Right. Well, you
Yeah.
notice, let me write that one. You'll notice a pattern. If you look at these three, you notice similarity that this one has 1, 0. This
Mm-hmm.
one has 2 zeros. This one has 3 zeros. So what would 40 dB have?
It have four zeros.
4 zeros or 10,000.
Yeah.
Okay.
Yeah.
See,
They're right.
they're not that hard.
No, if you can count right.
All right. Now, this one is special because there's a question. I consider it the hardest question on the general exam.
Uh-huh.
So you can either learn how to solve it or you can remember 20%.
Okay.
So what you have to do in this one is the anti-log. So they're telling you that you have a loss of 1 dB and they want to know what percentage loss that is in the question. So I know that a minus 1 dB, because it's a loss, so I've lost a dB, is going to be equal to 10 times the log of x. I don't know what x is, but I know that it's equal to the log of it's equal to minus 1 dB. So if I divide both sides by 10, I know that minus 1/10 is going to be equal to the log of x. So how do I find out what the log of x is? Well, I have to do the anti-log. And if you remember, all a logarithm is the power that I have to raise 10 to represent that value. So in the case of um, the 3 dB, I had a value of 2. The log turned out to be 0.3. So what that means is 10 to the 0.3, okay, is going to be equal to 2. And if you do that on your calculator, if you can raise um, 10 to the 0.3 power, it'll show you that the value is equal to 2. So that's all you're doing with a logarithm, is finding out what the exponent is, or the power of 10 that represents that number. So if we want to do the anti-log, we do 10 to the log. So in the case of our 3 dB one, we do 10 to the 0.3, and that's where we'd come out with 2. So in our loss problem, oh, this didn't come out right. This is supposed to be an exponent. It's 10 to the minus 0.1 power.
10 to the minus 0.1. Okay.
Right. I forgot to do the raise it subscript.
Yep.
So X is going to wind up being 0.794. If I do percentage, it's going to be 79.4%. Okay. But they want to know what the loss was. So the loss is going to be 20.6. Like I said, it's easier to remember 20%.
I think so. Especially right now.
Okay. So we learned that series circuits, the current is the same through each component. In parallel, the current's equal to the sum of the currents through the branches. Also in parallel, which we didn't mention it, I don't think they have a question that way, the voltage is the same across all the components if it's parallel. If it's
Yes.
series, the current's the same. If it's parallel, the voltage is the same. The current can be different. And RMS was the value of an AC voltage that produces the same power dissipation in a resistor or a load as the equivalent DC voltage. So your 120 volt AC house current, which is, they don't usually say RMS, but it's the RMS value, would has the same power as if you were running 120 volts DC. Of course, that doesn't work on motors, but it would work on some things. Light bulbs wouldn't care. If you put 120 volt DC on a 100-watt light bulb, you're going to get 100 watts out of the light bulb. Okay. Power is just the rate at which we use energy. And that was Joule's law, where we come up with the E squared over R, or I squared times R, which you'll need to use in a couple of the problems. Peak envelope power was the maximum instantaneous power achieved when transmitting. And remember, it's the RMS value of that instantaneous peak. That confuses a lot of people, the way they define it. And that the peak envelope is equal to the average, or RMS power, when it's unmodulated. And the decibels are 10 times the logarithm of the ratio of two values. If the values are positive, or excuse me, if the values are greater than 1, the decibel value is positive. If the ratio is less than 1, it's going to be negative. Any questions on those before we questions?
I guess not.
And they're not hard except for the one.
No, yeah, and I got a new calculator, and the log isn't working like my old style calculator did. So
Yeah, every calculator seems to be different.
Yeah, I'm used to I have a Hewlett Packard, with no equal sign. And so I'm used to that. But it has memory and program. You're not supposed to be able to have something
Right.
where you program to go for the test. So I said I'd get a little Texas Instrument, and I'm having more trouble with that part than the actual math.
Yeah.
But
This is the one that's kind of recommended.
what
Use
number is that? A 30?
it's a TI 30X 2S in this case.
That's what I have.
Okay.
I've got that. So that's what I'm learning. So good. Since you're familiar with it, you can help me.
Okay. All right. So what dB change represents a factor of 2 increase or decrease in power?
That's the 3 dB kit. You talked about that.
Is that the answer?
I'm going with Bravo
All right.
because you actually didn't you have that somewhere?
Yeah. Oh, yeah.
Yep.
How does the total current relate to the individual currents in a circuit of parallel resistors?
In parallel, that would be the sum of going through each of the branches, each of so Charlie, hot dog.
You're on a roll. How many watts of electrical power are consumed if 400 volts DC is supplied to an 800 ohm load?
400 TC, 800 ohm.
Yeah, so you don't know both voltage and current, you know voltage and resistance. And what formula do we use for
So
power?
that you have to square the voltage. No, yeah.
Right,
And then divided by the resistance,
right.
200. So Bravo. Yes? Hot
And you
dog.
didn't use your calculator.
Yeah, I probably should. I should not trust my math.
How many watts of electrical power are consumed by a 12 volt light bulb that draws zero point 0.2 amps?
So you have voltage and you have current. So they're times by each other. So um, I'm using my calculator. So you 2.4 alpha.
All right. How many watts are consumed when a current of 7 milliamps flows through a 1250 ohm resistance?
7 milliamps.
So remember, you got current and resistance.
So we have current and resistance. So you have to square the current, and then you have to times by the resistance. So and you're doing milliamps to ohms. So that should be milliwatts. So I'm going with alpha.
Well, let's see how you're doing.
Oh, hot dog. It's so
Yeah,
much
that one
easier.
that one can confuse you on the calculator if you're not
Yeah,
familiar with it.
because it's this, you get two of the same answers with just milliwatts versus watts. So if you're just looking at numbers, you can get hung up.
Yeah, they do those things to confuse you.
Thanks a lot. That's if I need help with that.
What is the peak envelope power produced by 200 volts peak to peak across a 50 ohm dummy load?
Now I don't remember this. So you had peak 200 volts, peak to peak across
Right.
50 ohms, dummy load. I don't know the formula. I don't remember this. Sorry.
Okay. Well, remember peak envelope power is the RMS power. So I got to convert my 200 volts peak to peak to what voltage it is RMS.
Which is the voltage times the 0.707, right?
Which voltage? Peak to peak or peak?
Oh, that's peak.
Right. Okay. So I got to divide by 2, right?
Oh, okay. So that's 100.
Okay. And 0.707 times 100.
Well, 70s.
Okay.
And then, so that's your peak power. That's your voltage power, peak.
Right.
Okay. And then you're going to,
Square it.
so you get back up to, so it's 100 watts, right?
Yep.
Hot dog.
That's a hard one too.
Yeah. So you got to remember the PP is not the VMR. Okay. I got it. I think I got it.
Yeah.
So you got divided by the resistance. Okay. After
Yeah.
you get to peak.
Yeah.
Got it.
Yeah.
Ooh, Lord.
Most people get confused on peak envelope power because they forget you got to use the RMS voltage.
Yeah. Okay. Got to remember that.
What value of an AC signal produces the same power dissipation in a resistor as a DC voltage of the same value?
That's the RMS, Charlie. That's what you've been saying.
Right. If I say it often enough, you'll remember.
I might.
What is the peak to peak voltage of a sine wave with an RMS voltage of 120 volts?
So that's
Now you got to
100.
do it backwards,
Yeah, I don't know if I can do that. Let's see. So we have a RMS voltage of 120,
right?
and that would equal, well, heck, I only have
0.707 times the peak, right?
707 times the
Times.
peak.
So,
So is that the 120?
so 120 is equal to 0.707 times V peak.
169.7. So that's Baker. Bravo.
Okay, now was that the peak or the peak to peak?
70 RMS. That was peak, but it wants
Okay,
peak to
it wants
peak.
peak to peak.
Oh,
So
good
what do
grief.
you do?
So then I have to do that square. No, that's not right. Now I'm all mixed up in my formulas here. Where's my formula? So you have to, so if I get the 169, hang in there with me, point
No problem.
0.7. And then I have to do, let's see here, hold on a second. Let me clear this. So you have double, so it's the delta. Whew.
Yeah, now realize it's talking about your 120 volts in your house, where we talk about it being 120 volts RMS. It's 340 volts peak to peak.
Hmm.
Most people don't realize it's that high a voltage.
No, I didn't either.
Okay, what is the RMS voltage of a sine wave with a value of 17 volts peak?
Peak. So So it is RMS voltage of a sine wave, 0.707, with a value of 17 at the peak. So 7. 14. Bravo.
Bravo. What percentage of power loss is equivalent to a loss of 1 dB?
Power loss. That's that 20.6, Charlie. Yeah, I got to remember Charlie because I ain't going through that formula.
Well, now it won't necessarily be Charlie.
Oh, I understand. Yeah, 20.6, 20.6.
What is the ratio of peak envelope power to average power for an unmodulated carrier?
Ratio of PP2. Isn't that the one? Baker? Bravo. Bravo.
Yep, they're the
For
same.
unmodulated carrier. Yes, I remember that.
What is the RMS voltage across a 50 ohm dummy load dissipating 1200 watts?
So we have RMS voltage
We got, yeah,
would equal.
resistance and power,
So we have resistance and power.
and they want voltage.
So that would be, wait, no, RMS voltage across a 50, that's there, dissipating 1200 watts. Um, two, four, 245, Baker. Bravo. I was hard time with that. I don't know that I got that formula though right because you had to square it divided by R. Okay. And then square root it again.
Is that what you did?
I think I did.
We got the right answer.
I did. So, but I actually got 24. So I didn't do something right. I don't know. I didn't punch in the numbers right.
Oh,
But I had the right formula though. The P, which is current, voltage squared divided by R, right?
right, right.
I got that.
So multiply 50 times the power is equal to the voltage squared.
And then you had to square.
And then the
Somehow
square
or
root
another, I got
of the
20.
voltage is going to be
Yeah.
equal to the square root of that big number.
Somehow or another, my decimal is wrong. But anyway, I'll figure that out.
Okay.
Practice.
What is the output peak envelope power of an unmodulated carrier if the average power is 1060 watts?
Well, the unmodulated character was the one before, so it should be the same. So it should be the 1060 watts.
They didn't trick you, did they?
They tried.
What is the output peak envelope power of 500 volts peak to peak across a 50 ohm load?
Peak to peak across a 50 volts, peak to peak across the resistance. Clear. Keep forgetting to clear this thing. $14 and the formula. Oh no, I got the wrong number. I picked up numbers that are not even on there. Um, so the 50 volts peak to peak,
No,
that
500 volts
500 volts.
peak to peak. So that would be 250 peak times 0.707,
Ah, that's what I did.
which is going to be somewhere probably less than 200.
Team. And then, so I'm not getting any of these numbers. So work me through this one, please.
Okay.
I don't know if my brain's getting fried or what.
All right, so we divided the volts peak to peak by 2 to get
peak to
peak,
peak.
right?
So that's 500,
And multiplied it by 0.707 or divided it by the square root of 2, whichever way you want to do it.
right?
Okay.
So that
So
gives you,
that gives us the RMS value of 176 or 177, round it. So E squared over R. So we square the 176 and divide it by 50, and you should come out with 625 watts.
I forgot to square it. That's why I wasn't getting any real number
Okay.
or a number that I thought looked right.
Yeah, you should come out pretty close. If
Yeah.
you're if you're not, then you did something wrong.
Yeah. It just looked like I was doing something wrong there. Okay. I got it now, though.
Okay.
Whew, I think my brain fried on that one.